Hello everyone. Today we start this lab where we design the control system. Now this is your lab is about designing different controls. So if we look at the start, this is lab number 12, design controller using root locus. So actually there are different types of controller. The main idea you have to remember is that whenever you need to improve the steady state error, you have to design PI or lag controller. When you have to improve the transient response, you have to design PD and lead controller. In some cases, if you need to improve both a steady state and transient response, then you use PID and lag lead network. Now the main equation is this one where you have to calculate the zeta using the overshoot information. So this is the formula that is used. Now we directly go to the cruise control example. So this is first order transfer function 1 over ms plus b here. Now what m is given to us, b, and input is 10 and output is the velocity. Now this is the specification that we have to meet, that rise time is less than 5 seconds, overshoot is less than 10, steady state error is less than 20. Now first of all we see how we design a proportional control. When we introduce a proportional control, the transfer function, closed loop transfer function, becomes kp divided by ms plus b plus kp. Now how we design a proportional control is very simple. Just enter mb, then numerator denominator to make the open loop transfer function figure, then plot the root locus of open loop, and then use s grid to plot the zeta and omega. And so this is zeta that is calculated from the 10% overshoot using the formula, and formula is also given in your book on page 180. If you look here, this is the formula to calculate the zeta. Now after this, what we have to do, we have to use the R locus, because we have to find the k so that we can satisfy the requirement. Then we have to plot and see that either or we are getting the result or not. So this whole code is about the step response. U means that you want 10 is the, and this is the axis where you want to see the response. So now if I go to Matlab quickly, so this is what I did: clear all, then I close all, then I clean the workspace, then I define s function, then mbu, then numerator denominator, then figure, then axis, then locus. So this will, till now, if I run it, okay, so it will plot the root locus. So this is the root locus, okay, for the open loop run, because it is the first order, so only one pole here. Now I look at the performance requirement that I print using s grid here. So when I do that on the same figure, I have this is the requirement. So this means that I can choose any value of k on this side. This will satisfy this criterion, okay. Now after that, I have to use a command that is available that will help me to find the locus. Value of k on the locus is known as rloc find, okay, where I have to give the numerator denominator of the open loop transfer function. Okay, when I do that, I get the kp value. After that, I will make a new figure and plot the step response. So if I run whole code here, this code is available on your lab. So look here, this is the one that is giving us the opportunity to do that. I click here, it will give me the selected pole location, okay, and also the kp value. and when I plot it, I get this result. No, there is a steady state error here, but overshoot requirements are fulfilled. Now this is the way you can design your proportional control. Now I quickly move to the next task. So next is that because there are still error, steady state error, as you see, now I move to next control. There is a lag controller, so that I can remove this steady state error. So you have to remember one thing, that whenever you design a lag controller, you didn't zero the steady state error. Instead you approach steady state error to 0. So in lag controller, you remember that you have to introduce a 0 and a pole. So why we call it lag? Because angle is negative. So how we design this? So I include this with the open loop transfer function. This is become the second order system here. Now I have to find the values, because I also have to multiply the proportional control. So this is the whole formulation what I get after with the closed loop transfer function, including the proportional control. Now again I create and hold off. Okay, so this is the open loop transfer function till here. Now because I want improvement in, so I put 0 is at 0.3 and pole at 0.03, so that the difference between and pole 0 ratio is 0.001, so that it's very negligible, that it didn't affect the transient response. So that's why I put 0 at 0.3 and pole at 0.03. okay, now then I hold on, then I find the k value, then I plot the step response. So if I move to my Matlab, so this is what I did again. Here this is where I put the lag controller, because I just want the ratio is 0.001. so if I run this, now again look here, now this is because of these poles, this what I get. Now if you see, this is the line semicircle, and this is the what you say, overshoot criterion. Now if I pick any value of k here, so these are the pole locations. So this is, look here, now error is almost 0 here. Okay, steady state error. So this is the way you can design your controller. Now if I just click on it and look at the peak response and click on it, on this peak response, so it is, overshoot is 10.2. okay, so I have to redesign it. This means that my overshoot criteria is not meeting, that must be less than 10. So that's why what I do here is again run it and put my angle somewhere here. Now it's 10.1. so this is the way you can use this. These are your closed loop poles that you selected. So this is the way you can design your controller using lag controller. Okay, now if I quickly move to the next task. So next task is a bit creative one. This is the example where we have to design the PD control. If you remember the PD control, the main idea behind PD control is to introduce a 0 in the system. So how we do that? So this is our open loop transfer function. So now PD actually improve the transient response. So how we do that? Simply we plot this, the open loop transfer function here, locus, then look at the zeta, that is given to us. Now we want to reduce the settling time as well. So what we did, first of all, we have to use the ASCII and plot the root locus, and then use our local find to calculate the k value. Okay, now when we choose the pole here, which pole I want, because there are 3 poles here. Now we have to choose a pole. From these poles we use this formula to calculate the settling time, peak time. So what this formula is, 4 divided by real part of the pole, that if you remember that settling time is equal to 4 divided by sigma. Sigma is the real part of the pole. Similarly, peak time is actually pi divided by imaginary part of the pole. So percentage overshoot is POS, that is calculated using the formula that exponential of minus zeta pi times zeta divided by square root of 1 minus zeta square and times the 100. If you remember, this is the formula that you have in your book on page 180. This is the formula that they implemented. Now after that you calculate the gain, KP, that is the DC gain. What is the actual gain, that we call it KP. Then you calculate the feedback with that K. Now after that you plot the step response and look at the damping ratio. Then you have to design this PD control. So the main idea PD control is to put the 0. So that's why a while loop is here, and he is asking you to find the location by working yourself and let him know what is the location where you want to put the 0. Now after that, when you do that, he just multiply, because cascaded with the transfer function. Now then he calculate the what you say omega n, because zeta is given, you have the settling time you want, then you find the R locus and then ASCII. Then using this you can choose the K gain controller. So this is the main idea, and this whole is working on it. Then it allow you to do it again if you think that satisfaction is not done for PD control. So this whole script is about this. Now if I go to my command window and do it quickly, and this is, I think, this one. Alright, so this is the main code here. Okay, so if I run it, okay, this is the with zeta, and you have to find this is proportion control design. So if I choose something here, now he asked me which pole you want to choose, because if you remember, I told you that using these pole location I can calculate the settling time and all other informations. Now I say, okay, choose the first pole, that is this one, that is the real one. Then he asked me, okay, I choose it. When I choose this pole, this is the closed loop transfer function, and before that this is the value of the gain, that is nearly 5. Now if I press it, it will plot the step response. So this is the step response that I am getting with the controller. So you can look at the characteristics here. This is overshoot and things like that. After that I have to plot the PD control. I press it, then he is asking me where you want to put your 0 here. So for that 0 you have to know the what you say where you have to put. For example, I say, okay, put it at 5. Then he says, if you are okay, you are done with it, because when you put it 5, this is what you are getting. Now I say yes. Okay, this is what is. But the thing is, this is not a good choice because your hole is within the criterion. So if I put some value here and I say I am interested in first pole, then this is the whole code and this is the result I am getting. If you look at the peak response, because it will improve, that need to be less than 5 and it is satisfied in this case. So this is main idea in your lab number 12. Now if I move to next thing, is saying question number 1. He's saying that this is the transfer function open loop HFS given, design a compensator that yields percent less than 10%. Okay, how we do that? So it's very easy. So if I move to my lab number, let me open this question here. This is fourth one. If I did it, yes, this is question number 1, gain controller design. So I put G, H, then 10%, then I put this formula to calculate the zeta. How I get this formula? I told you again, go to your book, page number 180, this is the formula. Okay, now after that what I did actually, plot the R locus of G time H, because H is here, so this is the open loop. Then S grid with zeta omega n is not given, so I put 0 here, used input. So this is the formula R locus to find the gain. After that I plot the step response. So if I run it, this is what I get. So this is the criterion. If I choose something here, this is the point and this is the percentage overshoot. Hopefully it will satisfy it. Yes, 10% overshoot. So this will satisfy. If it is not, you have to do it again, and this is the way you can design your controller. Okay, these are the closed loop. You can move these closed loop further here. Now last question is similar to example of PD control, and he is asking us to do it, to design it with same criterion, that 5%. So if you do the same coding, but you have to do it using similar example, but y of t is instead of c. So what you have to do, you have to remove this s here. Okay, now what I did here for this question number 2, I quickly make a small coding here. So look, this is the G, I remove S here, this is the H, 10%, zeta, everything is similar. I run it. So look here, this is GH. If I choose something here for gain control, so this is what I get, and it satisfied all the conditions. Okay, now this is one way of designing it. So there's another way of doing it which is much easier when we have to design. So it's known as scissor tool. If you write a scissor tool, you open with this window, scissor tool, and from here you use the import. So import, you have to click here and browse it. You can browse the value from the workspace H and G here. After that, when you do that, so what you have to do, you have to right click here and include the design requirement. Now put new requirement and put the settling time, then add, then say okay, then put the next one, add a new design requirement, so on. So this is a very easy way to include. So I include all these design requirements. Now I have to design a PD control here. So what I do actually here, if I go to design, edit compensator, so this is my compensator that I design. Okay, So what I did here, I just remove it here, so that I tell you how to design it. And also controller gain is 1. Okay, now so this is what I get here. I just close the windows that are not required. So what I do here, I go to analysis and select the step response. Okay, look here, step response. There are 2 step response. I need 1. I go to analysis. Okay, I just need 1. So what I did, I just go to here and go to analysis plot. I just need only 1. I'm interested in input and output. So what I did here, I do one thing more. I just say none here, so that I need only 1 plot here. So I go to analysis plot. So this is the one. All right. Okay. Now I say minimize here. So this is the analysis plot. So what I did, I just extract, and just if I make a new requirement, I just, if you look at your task, rise time is less than 5. So what you have to do here, you have to go to rise time. Rise time is not there, natural frequency is there, so you have to put natural frequency calculating from rise time. Then overshoot, so percentage overshoot is given here. So percentage overshoot is, for example, less than 10. You put and so okay. Then again you add a new requirement, that steady state error. So steady state error, settling time is there. Steady state error is not here. Okay. Now when you put all these things, so these are the design requirement, and this is your open loop what you say, root locus. Now if I open with them, this is the criterion. So when I do that, rise time is 6.15 and final value is 0.4. Actually the input is the 1. So steady state is not meeting, rise time is not meeting. So what overshoot, actually there's no overshoot, so there's not a issue with the overshoot. Now I have to design a controller. So I need to, for PD control, I need to put a 0 here. I add 0 from here and put here. So I put somewhere here. Okay, look here, I put the 0. Now after putting 0, so this is updated again, nothing is changed. So I have to choose here, select here the closed loop poles. When I do that, I move it towards the 0. So look here, my rise time is nearly satisfying. My final value, I need a 2%. So this means that something I need is 0.98. Look here, so it is 931. If I move further, now if your rise time is less than 5 seconds, 10% and 2%. Now if you look here, so it's very easy using CISO tool, and I just go a bit further. So if you, this is within 2% of final value. So if I check the overshoot, settling time is also satisfying. So this is the way you can easily use CISO tool to design your controller. So I will stop here for this video. Thank you.